Robots are an invaluable asset in remote environments as they can keep humans out of danger. Here we have a remote platform where robots are expected to inspect and maintain it autonomously, whilst communicating with remote operators through a human-robot interface. Using semi-supervised learning from demonstration, a robot can learn from a mix of labeled and unlabeled data to navigate and operate in a dynamic environment. Explaining the behavior of the autonomous robot is challenging. Even experts may fail to communicate the decision-making process while controlling complex systems. Robot operators use an array of interfaces to check what the robots are doing and need to understand their reasoning in case they have to intercede. This is made even more complicated by the multiple types of robots with different behaviors. Here we present a system for self-explainable robots that synthesizes natural language reports about what the robot is doing and why. The reports are simple and straightforward, designed to keep the operators informed without overloading them with information. They work as an add-on to semi-supervised learned models that control the robot, and are model and domain agnostic to keep them flexible in dynamic environments. Let's dive deeper into the system. The first part is to learn from a demonstration. The operator remotely performs a demonstration of what the robot should do in the platform. From the demonstrations, the system is able to extract high-level goals and train a neural network that predicts the operator's actions. We use the goals and the neural network to autonomously control the robot and synthesize more complex behavior based on the combination of the goals. The path towards the goal is generated dynamically based on the obstacles that the robot detects in its surroundings. Next, using the model and inferred goals, the system can perform inference analysis. The most important are the sensitivity analysis to detect salient objects, so those that most influence the robot's path predictions, and counterfactual analysis, which allows the system to check for modifications of the scenario that will solve the task. As the high-level goals, object saliency, and behavioral prediction are in the state space, they can be directly represented as marks and figures in the sensor images. To improve transparency, we feed these data into a natural language generation module to produce reports in natural language about what is happening and why. This allows for the display to be much simpler, and thus it can reduce the information overload of the operators of these remote autonomous robots.